I should be sharing on the screen. Our lesson goals are basically up there at the moment, okay? So we're going to be talking about power today and how power is used and affected within our data centers. So first of all, let's liven up a bit. Let's have a thumbs up for everyone that can see that lesson goals within the Zoom window. We do a fastest fingers first. Thank you very much, Christopher, in there. Teng, Fatima, Raphael. Okay, good. So we're all in there and looking at the right presentation slides. That's good. There's a bonus if anyone sees me doing anything slightly wrong. No, only joking. You will notice me flicking from side to side. My live chat is on the window over here. Some of the presentation is down there. Some of the other stuff is elsewhere on the windows. Please don't get too distracted by that, I hope anyway. And let's see what we can talk to you about today. So as I said, we're going to talk about power, the electricity stuff that comes into data centers and how that's actually used. So we're going to gain a comprehensive understanding of the power sources and also the data center tiers, because they break them into tiers, which is quite important. We're going to recognize the critical roles of electricity, loads, PUEs we're going to introduce you to, current, the different types of power that we have, AC and DC, we're going to have some conversations about as well. And we're going to develop some skills to effectively monitor and perform fundamental maintenance tasks on those systems. So power outages, this is why things are so important. We kind of begin this lesson with a look at something that's basically on there. So there's an introduction and a directory. I hope you all are able to access the Codio session. And if you have the Codio open, you'll see directly in the introduction and directions, there is a small article in there. If you can all see that article, if you can click on that article, and then we're going to have a little look at these subsequent questions. So we can sort of read it together, but I'm going to give you a head up on some of the questions we're basically going to ask. What we're going to ask in this particular session is that example gives us a real life issue that literally happened to some data centers. Okay, and we're going to look for these questions. What are the primary causes of the data center outage in Texas? How did the extreme weather condition affect the operations of the data center? There's a link for the article from Megan. Thank you very much. What role did the generator fuel delivery issue play? How did the data center operations manager, or sorry, operations manage to secure their fuel? How did they go about that? How did they make sure their systems were up and running? And essentially what lessons you can read from that. So if you can all just pop that open, have a quick read, see if you can answer those particular questions. We'll leave those up there at the moment. And I'll give you a couple of minutes just to digest that. Please, as I say, feel free to poke any questions into the live chat. I'm going to have a sip of coffee every now and again. You will notice that as well. Now, while this is sort of an edge case, it's certainly something that could well happen. Victor says, what he says is negligence. Fail to plan, yes. Fail to plan, plan to fail, isn't it? Certainly, I think in Texas, they probably don't expect to have such a cold snap. This is all probably part of the changing weather climates that we have. But as a data center manager, you certainly got to be considering a lot of these items, haven't you? Moody says it was due to the temperature plunging. Well done, definitely in there. So we're looking for primary causes there, weren't we? Daniel's a native-born Texan. Well done. He says, "What's a cold?" Yeah, exactly. And Texas is one of those places you probably don't expect. I mean, this is my geography is pretty. Oh, it's okay. It's pretty okay. My mum and dad used to work in the Met Office, so I feel I should know a little something about some of the weather. But Texas is probably one of those places you don't expect to have incredibly freezing snaps indeed. Bredo says temperature and the lack of planning to have fuel available for the generators. Risk assessment failures. Yeah, Annabelle. Yeah, definitely. We need to think about risk assessments when we're looking at data centers and the power that comes in. Greg's basically putting there not prepared for the worst case scenario. And when you look, it's interesting because when you look at things such as risk assessments, if you look at risk assessments as a manager, part of you goes in terms of how much is it actually going to cost me to prevent that particular risk from occurring. So if it's an edge case on the risk, you kind of go, is that likely to happen over 10 years? If the answer is no, then you can kind of accept it and go, you know what, we'll take it on the chin if that happens. But if taking it on the chin involves damaging your reputation and damaging your financial structure, you've got to weigh that damage against the cost of actually planning for that potentially not to happen, never happening item. So it's very good to bring risk assessment in there. Thank you very much, Annabelle. Some facilities experience issues. So, Gruda, sorry if I pronounce any names wrong here. Some facilities experience issues due to inadequate winterization, including manufacturing cooling systems and emergency generators. Yes, you've got to look after some of these things. We took climate change for granted. Bertrand says there, yes. Acts of God aren't the easiest things to prepare for. I'll just ask Noah, don't you, really? So those questions we said. So we're having a look here. So what were the primary causes of the data center's outages? We've got quite a few in there that basically talk about how did the extreme weather conditions affect the operations in data centers? Yes, it got too cold. The article, Annabelle says yes in here. The article suggests that it wasn't just about unexpected weather. It's about systemic failures to prepare for the forecast. Very much true, isn't it? And part of it was, of course, it wasn't just a short stay of weather, was it? It was extended as well. I believe if you read through the article, there's one guy that basically had a agreement with a fuel provider that made him their priority. And because of that priority, he was able to get fuel while a lot of other places weren't able to get that all important fuel to run the diesel generators while the main power was basically out. Fuel distribution, well, Anna Keen, yes, fuel distribution key. If you can massage that relationship before something happens, when it happens and goes wrong, yes, then you have an agreement in place. You have service level agreements with the fuel providers that says if we press the button and ask for that fuel, you will deliver it within X number of hours, days, basically top priority, isn't it? Stefan basically puts a very valid point in there. Texas, you don't expect the snow, so you don't salt the roads. So if you do have issues, they're not sorted. You're not prepared to roll out big salting machines to make sure the roads stay open and get on with things. And the fuel quality was an issue as well. Yes, if they're scrambling to put any fuel into those generators, then potentially you're going to get generators failing. And again, we'll talk later on about how many generators you need and what a generator number plus X basically means to them and how this basically affects your data center. Question number 5, basically, and there talks about the cooling systems. How would it affect the cooling systems in there? And indeed, on Thursday's lecture, we do cover cooling systems in some details, but have a little think about some of that and how that would affect you as well. Christopher says, fuel quality, no power, no cooling. Yes, exactly. You can't cool things. Sometimes it's a case of where you divert power. We basically deal with switching systems that can basically control where the power goes and which are your priority systems. Certainly if it's freezing outside, yes, how does your cooling system behave? If you've got something like a water-cooled system, how's that actually going to affect your water cooling? Are your pipes insulated, or are you simply going to have your water cooling system freeze over? Yeah, cold compresses materials and causes thermal stress. Man, Stephen, sounds like you've done a degree in something like that. Very good. I like that one. Thank you very much. Pipes can burst. Yes. Okay, should we have a quick thumbs up? Who's basically managed to complete that? I think we're doing pretty well going through that. Well done, people. Blocked airflows. Yeah, definitely blocked airflows are keen. Systems, yeah. Certainly the systems, Yinka, I hope I got that one right. Systems weren't designed to operate in such temperatures. Okay, again, a systemic failure. We're going to look at what we're prepared for, don't we? Okay, so if you can finish up reading that, I'll give you another couple of seconds. And then we will move onwards. I know people read at different speeds, so it's obviously quite entertaining, isn't it, to go through those. But you can see here what they've basically had is they've had a non-normal, probably the best way to put it, weather climate event basically happening in the area. Everything's frozen, the electrical power system's gone down, and they then fall over to relying onto the diesel generators. Who can get enough diesel to their diesel generators in time? I know in IMART, when we were working with IMART in the UK, the main data center, which is actually up in Maidenhead, they believe their diesel generators could potentially work for 48 hours without being topped up with diesel. But at 48 hours, if you haven't got more diesel trucks coming in, then all of a sudden you're probably going to be in problems, aren't you? So thank you very much for glancing through that one. Anyone got any questions about that one? Victor says, in the end, was planning for the future, not using past data such as, hey, we had snow in 1970. It was 30 years ago, wasn't it? 30 years ago, you had snow. Most executives will sit there and be going, I'm probably not going to be in this company in 10 to 15 years' time because they normally move along that sort of time. Why would they build a risk assessment for that, eat into their profit? But you're right, it is all about planning for the unexpected. And this is where we talk about backups and redundancy systems. You're not planning for things to fail, you plan for things, yeah, you're not planning things to work properly, you plan for things to fail. And that's the important difference around everything there, isn't it? Okay, no more questions coming through. That's great. Let's shuffle on to the next one then. So let's have a look at the power in the infrastructure. We know data centers need electricity. We know they need lots of electricity. Okay, and without electricity, the systems fall over. So they are massively important for the power systems. You've got to make sure that you are covered belt and braces. So your power infrastructure in your data center must be able to cope with the power that you need in the data center and extra pieces. So additional components in there are things such as power generator sources, tend to be things such as your utility grid, generators, renewable energy is used as well. But we also need to distribute that power within the data center. So we have power distribution systems such as transformers, switching gears, and distribution panels. And we'll go into those in some more detail as we get through the lecture. And the whole idea when we're thinking about power within the data center is to minimize the risk of any form of outage. Okay, so it's important to think of redundancy, redundancy, and redundancy is literally what we're going through. So generally what we have, we all know we basically deal with electricity that comes off of the national grid. So if we're a data center, we would probably have two pipeways coming in for our national grid. IMART basically had two systems of electricity coming in from two separate substations that were local substations, but they had them coming into the building in two separate directions. So someone with a digger couldn't go through both, hopefully couldn't go through both, because they'd have to be digging two separate holes. Okay, that's an example of building in some redundancy. Yes, it costs them loads of money to basically get it put in to start with, but the benefit of having a second source is essential. We have things like UPSs, uninterruptible power supplies. So let's put a hand up. Who's got an uninterruptible power supply or has seen a UPS before? Garda basically says, I did. Was it a big size UPS or was it a server racked one? Patrick's got a small one hooked up. That's good. Power banks don't really count unless they can run your systems. But yes, I mean, essentially, we all carried around essentially what we could be considered to be a UPS battery, which is basically in our, in a power bank that we carry for our phone. So if our phone runs out of electricity, we can plug that in. Hey, that's basically a backup battery. Okay, we are dealing redundancy when we are doing that. Oh, Victor was born in the Dominican Republic. It's mandatory for home systems too. Is it mandatory you have a diesel generator? Is that what it is, Victor? A UPS, so a battery, a big, massive battery set, yeah? Or is it a UPS that we term as a diesel generator? We're going to make a separation between the two in a minute. UPS, oh, definitely. Stefan there basically says, what about diesel generators? Yeah, okay, we term diesel generators are normally roped into what we term as a UPS, an uninterruptible power supply, because they form as a backup solution for it. I'm old school, so I tend to consider a UPS a battery pack, a group of batteries, and we'll go into how many batteries you have in those as well. And a diesel generator then essentially takes over from the battery pack, and we'll talk about how things fall over and what things basically happen. Now, we know electricity is important. More is always more when you're dealing with looking after your electricity system. So there's the electrical distribution system. This is a substation. Very nice picture of a substation. So this basically comes off the main grid. Okay, and the main grid basically powers down to these smaller substations And the smaller substations then basically divert the electricity to whatever is basically using it. This can basically be to factories, to data centers, and indeed to domestic locations as well. So they have big substations and they have little substations. They have major ones as well as minor ones, and it tends basically to come down in grading. So you basically have the electrical generation system that happens to be valid in your particular country or state. And that then basically gets reduced down to a main substation that then forks out into lots of small substations depending on your location. And of course, you pay for these guys to deliver electricity. So yeah, that's hopefully what you do. So when that comes into your data center, it comes into essentially something which will be located such as a switchgear. Okay, this includes high and low voltage switches to protect circuit breakers. Okay, are in there as well. And this allows isolation of equipment for maintenance, so you can shut off certain sections without having to cut off the whole of the power. So you can cut off particular rooms if you have it like that, and you can cut off particular racks in rooms, depending on how your system is set up. But you'd normally expect to be able to not just shut down an entire room in a data center, you'd also expect to be able to shut down an entire row of server racks. And that would normally be on its own switch center. In fact, it would probably be on 2 switch centers from 2 separate switch gears. So you would have 2 power systems running to that rack, that line of racks anyway. And it allows us to safely do this without any issues. So not only do we have these small little areas, we have something called a transformer. Who's used a transformer? Put a hand up if you've used a transformer. No, I'm going to be honest here, it's a bit of a trick question I've thrown out there. I'm just looking around actually. Dangerous? Transformers aren't dangerous. You've seen a transformer, Bertrand? Yeah. Younker's seen a transformer. I've seen one. You don't normally interact with it. Yeah, Hugo, you don't normally interact with your transformer. Patrick says, I support the power I'm currently getting comes from one. I suppose, yes. This is why I'd expect everyone to put their thumbs up. If you're running on a laptop, your laptop power goes through a transformer, a former transformer. Of course, it's not as big as we see in a data center, but let's be honest, the device is, oh, this is where I drop it, I have some problems. That's a transformer. That basically chops the voltage down from my AC so that my laptop can basically use it. So that's a tiny transformer. You see in the images we got in the picture there, these are big style transformers. And we'll talk about how transformers basically run a little bit later if you like. Yeah, the power brick. Simple as that, Stefan, isn't it? I say thank you. We do like the comedy in there. Thank you very much, Gerda. Yes, I know we're going to get loads of transformer pictures now. Thank you. Okay, so normally what they do is they are designed to take a voltage and they are designed to step it down. And we will go into what voltages is and what voltage we tend to supply and how it gets stepped down a little bit later. So we will cover some of that, which is great fun. But they must be sized for both the current and the demand for future growth. There's no point putting in a transformer that's good for now, because we know in 5 years' time, we're going to want a load more power, basically powering our data center, because our data center is going to expand. What we need to run servers and things is potentially going to go up. And that's the idea. We expect our data center to grow. So we basically want to make sure we size it for both current demand and for the future. And you'll find out that's the case basically for an awful lot of stuff, isn't it? We also in our data center have things called panel boards. These are dealing with routing and distribution of power branches. So we can basically isolate different locations. Our panel board provides metering, grounding, and essentially overcurrent protection. So the panel boards, if you've got a domestic house, if you're in a domestic house, your panel board, you might consider to look very similar to your fuse box. Okay, because it will have fuses in it. It will have what's known as RCD systems in there. Okay, and we'll talk a little bit about RCDs a bit later as well, covering some of the highlights here. Then we have transfer switches. These are the devices that do a lot of the hard work. Okay, transfer switches will literally quickly switch the power over from grid to UPS to generators. Now, I do mention it in that particular order because how quickly does a generator start up? Now, that's pretty much a rhetorical answer. We know a generator is basically a massive diesel engine. Okay, so your diesel generator. Imagine how quickly does your diesel car start up, unless you've all got electrics now. So your diesel car doesn't start up automatically, does it? You put a key in, you turn it, doesn't kick over straight away. It can take 5 seconds, 10 seconds, 2 seconds. Okay, so it can take a little bit of time for it to kick in. So normally what happens with a power failure, and we've experienced this before, is that your initial system will fail, which is the grid power that comes into your data center. The transfer switch will click across and go, right, God, I've got to go to my UPS, which is our mass of batteries. So the battery pack will kick in. At IMART's main data center, they reckon they could get 30 minutes out of their batteries, and that is it. Okay, so if their diesel generators didn't kick in within the 30 minutes, thank God they were good, then the data center would be dead. Okay, that's your battery storage. Good. Any questions around that? So the idea is that it switches from the mains, which is your grid system, onto the batteries while it basically stays up and running. And then when the diesel's generators are able to take over, it will take them over. Now they have to be fairly smart. And we'll talk about this. Yeah, let's open this can of worms now. Let's open this can of worms now, shall we? Okay, so the electricity that comes into your data center, indeed into your houses, indeed into everything essentially, from the national grid is AC current. And we're going to what AC is later. So it's an AC format current, which is a wavy current. Your batteries, of course, are DC current. So our transformer is switching from an AC current to a DC current, and then back to a generator, which is an AC current. So they are smart things. They do know what they're doing, and they can cope with this when they basically flick across the switches. So the other couple of things you're likely to see within a data center are going to be things, they call them busways, okay, conduits. They're basically big locations where you put cables in. I have seen the cables in IMART, and they've got a special room where all the cables come in. And just to impress everyone, rather than having the regular floor panels that are nice solid ones, because of course it's a raised floor, they've actually got some that are glass perspex that you can see through. So they'll quite often take you into one of these rooms, similar to this one, that has got some glass flooring in it, and you can see the cables, the power cables. They were just ridiculously big. But they basically all got to go via conduits and busways. The flexible power conduits basically get you to your circuits. Last but not least, we have a power distribution unit, okay, which is normally located in the rack. PDUs, okay. Yes, that's right, Annabelle. So PDUs are power distribution units, which basically enable and monitor remote control of individual outlets. So when we talk about data centers, depending on how we're looking after them, how we are managing the electricity coming in, how many backups we have, what style of backup systems, we will get graded as a particular tier. Okay, tier 1 is fantastic, tier 4 is dropping down a bit. But when you look at the numbers between them, you'll probably be quite amazed as to how good they all are. And the idea is the tiers are demonstrating the reliability that will ensure that that particular data center stays up and running. Any questions about that particular part of the topics? We will go into more details on a lot of this stuff, but please, more questions is better for me. Good stuff. Let's pop on to the next item then. So mains power. Let's talk about the mains power that comes into data centers, comes to the electrical grid. It is all AC. We use AC because alternate current AC is able to transfer across longer distances with less power loss, less issues. So everything comes into our building as AC. Yeah, I'm definitely speaking in English. Don't know if you got that flash up. So we convert that into DC power because the data center equipment, a lot of the modern data center equipment will use DC. Okay, we know that most of our PCs and everything like that, you plug an AC connection into it. Into all our servers, we plug AC connections. Switches and stuff is all AC, but it gets converted into DC when it's actually in the box, when it basically does all the hard work and everything like that. And that essentially is happening through our transformer that we spoke about. That not only steps the voltage down to something that our system can use, but it also converts it into a DC current. So backups. So we've spoken about UPSs, the uninterruptible power source, which is normally created initially from batteries and then diesel generators. And this is switched over with the automatic transfer switch, so the ATS switch. And all those panels basically put together give us a decent power source. So to give you some ideas, there's some beautiful pictures there of Drax, which is our diesel power generators. And they can be big, massive. I might have had 5 diesel generators. They were all situated outside the building and all situated in slightly different locations. So, you know, of course, if there was an issue in one particular area, such as a fire or something going big time wrong somewhere else, that the other generators would potentially still be okay and they wouldn't be affected by that issue. So, for example, if a lorry had crashed through the gate and smashed up a diesel generator. Well, there's so many green and orange pipes. Water cooling, diesel in. The big blue ones, I think, are air coming in. So the big blue one will be the air coming into the system for the generator. And certainly, I think the orange are cooling. I could be wrong there, I believe. Orange could be exhaust. You could be right. Well, you got to think, I mean, you look at generators, you look at diesel generators, they are just like your diesel car engine, but they are massive. They are a lot bigger. Okay, a normal diesel generator that we saw at IMART was about the size of a normal family bedroom, was what they were housed in. And let's just recap that very quickly for everyone. So we have 3 main power sources. Okay, there's the grid, national grid, that provides us the electricity. comes in straight AC. We have batteries as a backup, which essentially is our primary source that it drops over to. Okay, and then there's basically the diesel generators. Now, diesel generators will normally kick in within 5 to 7 seconds of a power outage. At least you hope, anyway. So we've got a discussion question here. So what if both sources, mains and backup power, fail simultaneously? How could we protect against this? Any thoughts? Please share it in the live chat. Second backup. Christopher basically says the second backup. Yep. Bertrand, redundancy. How would you manage the redundancy, Bertrand? Daniel is there. Head to local PetSmart for an extra hamster. That's probably a good one. Limited UPS supplies power. Yeah, Stefan, definitely. Your UPS, I mean, your UPS will manage for a certain amount of time, won't it? You know, and quite often you will see people going, there's panic when our UPS kicks in, because that means you've got a certain amount of time before your systems die on you. Frodo's basically said have gens. Yeah, generators are definitely in there. They're the backup, aren't they? Victor, we do cover the 2n+1. That's a problem. It's important to have a second of everything. So 2 sources of power, 2 backups. Annabelle in there as well. Well done. N2+1, good. Bertrand in there as well. Don't they have those batteries in trucks that pull up? I don't think they do. I don't think by the time they drive them there, they're probably already dead, aren't they? Stefan makes a very valid point, and with the regular testing for generators, and we do mention that later. Good. There's certainly a lot of good answers there. Who's done anything with Azure or AWS? Azure and AWS deal with this in a really attractive way, in that they have regions and zones. And when you do have something with AWS or Amazon or Azure, so Microsoft or AWS, they will basically break your systems into regions, and they'll basically put them in separate data centers. So they'll pair them across the data centers. So even if they do lose a data center and everything goes wrong at that data center, your system essentially is duplicated somewhere else. AWS has 3 buckets, yeah. Azure. So they have the regions and availability zones, don't they? They have parent sites, yeah. So you can do it if you want to do it. That's the big thing, big answer, isn't it? Here's a good question there, Gardar. General question: as the data center technicians, are we responsible for handling the electrical components of the data center, or is it more important to have a broad understanding of all the equipment used within the facility? It depends on the position you have. When I was training at IMART, the NOC staff, which are basically the Network Operations Center staff, we would qualify them in particular tools. So as you walked in green off the street, we wouldn't expect you to be in charge of the power systems. But as you basically got through, your time there, and we trained you up and we taught you things about the power systems, yes, then you would all of a sudden you get a tick in the box that says, yes, this person's been shown how to test the diesel generators, how to maintain the diesel generators. We're not talking about actually getting your hands dirty and getting a screwdriver out and taking them apart, but in terms of looking at them, test it, does it work? Yes. Is there any oil leak? Is there any leaks in the pipes? So general maintenance, you would get a tick in the box, and then you would go on the rotor to basically do that with the other knock staff. And it will be that sort of a thing. All knock staff will be trained in terms of isolation, so power isolations for room, for individual racks, and for rows of racks, so the aisles essentially. But as Victor says, a broad understanding, electricians do their job and their knock staff basically just point out what's wrong. So you get involved in the monitoring. Okay, so let's shuffle on then. So redundancy review. So starting out, what can you look to do outside of cabling and building racks? Depends where you start. Yes, a lot of people start at the cabling racks, building racks, sliding devices in. General maintenance you'll be doing, swapping disk drives out, changing memory, upgrading servers when required, repatching network connections. There'll be a lot of different things. It's probably not really covered for this when we're talking about the electricity. And when it comes to the electrical end of things, as a data center technician, your job will be to spot the faults and the issues, and that will be all done through some of the monitoring tools, and you will be checking up on the monitoring tools. So that will be your catch. You won't be expected to get a pair of cable strippers and go and repair some electrical wiring. That all gets handed over to a qualified electrician, a data center technician, a data center electrician. Those are the right words. So I'll answer that one for you, Nima. Right. Okay, so review of redundancy. Okay, if there's only one power source, if that goes, we lose power and we get a system fault. We have backups to the transformers that allow us to use different power stations. So this is the beautiful. Has everyone been reading ahead? And this is why we were so good with the n+1 and the 2n+1. Okay, when we define this, n is the minimum capacity needed to power and cool the data center. Remember, we've got to get it cool as well. Okay, so by default, you have n power generators. Okay, so a data center will essentially have a backup generator. This is called n+1. So instead of having, if I can run my entire data center off a single diesel generator, I've got one generator. If I want to go n+1, I then get another generator and stick it next to it and go, okay, if one of them fails, the other one's still going to be okay, and I'll still have my data center running. If I need 5 diesel generators to run my data center, and I want to go n+1, well, I just buy a 6th one. And that is n, the number that I need to run the data center, plus the additional 1. Or you could go +2, +3, depending on your multiple backup strategies that you have. And of course, it all comes down to that green stuff, doesn't it? Money in the end of the day. You can also go as far as to have a fully mirrored power system, and that is called 2n. Now you can imagine that if I've got 5 diesel generators and I want to fully mirror that power system, that means I've now got to have 10 diesel generators. And then if I do 2n+1, I've now got 12, because remember, I've got 6 on each. So these are a couple of examples of redundancy there. So n+1, if I have 3 UPSs needed, 3 diesel generators needed, n+1, 1 additional, total of 4. Does that make sense? Well, let's have a big thumbs up for that making sense to you all. I've got a question there. Should both generators in the data center set up be? Oh, I'm just laughing because you're making it scroll up. I can't see it off the top of the window. Data center setup be identical in terms of capacity, brand, and specification, is acceptable for them to be different as long as no, that's a really good question. Okay, in NATs, the UK National Air Transport Service that I've worked for, their data centers, their A and B, essentially their redundancy and essentially their 2N, so their second duplication, that is a duplicated power supply, they insist they are different manufacturers of diesel generators. And the reason they do that is because they don't want to get to a situation where they're unable to get that manufacturer out to repair it, unable to get the parts, or there becomes a security issue with some of the software that runs that particular side of the generators. Right, so if they've got a whole load of Volvo Penta generators on one side, they will go and buy a whole load of another company's generators to run the other side of the data center. And that way, if there's a massive issue with one load and they can't get the parts or anything, they know they've still got a full set of working generators with another company, with another supplier, with another service level agreement written. So they do it like that. Does that answer that one? That question for you? Gadar? Gadir? I'm going for Gadir. Great stuff. Let me know if I get your name badly wrong, and I'll apologize. We briefly touched on some 2n+1 methods in the previous lesson. That's fine. I thought you might have done. Good stuff. So let's have a look at some data center tiering. Okay, the tier system comes in to let a customer know when they come to a data center, what is the reliability factor of that data center? So there's a metrics that basically gets produced for the data center tiers, and it's all related to uptime. Because what do we care about as customers? We care about how much time our system is going to be up, or more importantly, how much time it's actually potentially going to be dropped. So the higher the data tier center, the more built-in redundancy and critical systems like power, cooling, infrastructure are in there. You know, belt and braces for all of those. So not just talking about power when you talk about a data center tier. You also talk about your bandwidth, your internet pipes that are coming in and out, as well as your air conditioning. So it all gets rolled into something, and it talks about an uptime. So you can see tier one there. Tier one, their uptime 99.671%. And you kind of think, wow, that's massive. That's great. But if you look at that, that's 28.8 hours downtime per year. That's a killer for a lot of 24/7 businesses. Okay, so tier four, which is where we tend to aim for, and a lot of people will tell you about these things, we tend to aim for tier four, is 99.995. 26.3 minutes downtime per year. Okay, which is slightly more acceptable for big businesses. Okay, anyone got any questions around that? Okay, I'm going to share a little video for you.
Hi, welcome to this video on data center tier levels by 4D.
Thumbs up if you could hear the sound. Oh, fastest fingers first there. Thank you very much, Kadir. Good, I'll let you get on with that then.
Today we're going to be talking about the different data center tier levels, what they cover and whether they're still relevant. So the data center tiering levels were first started by the Telecoms Industry Association to define 4 levels of reliability within data centers and how well they could survive a fault such as a mains failure or cooling failure. A few years later, the Uptime Institute brought out their version of the tier standards, which also covered 4 levels of reliability, but they also offered a certification option. And even today there's confusion between TIA and Uptime Institute standards. So what are the 4 tier levels? We'll focus on the Uptime Institute's tiering because that's the one that most people use. The tiers run through 1 to 4, with 1 being the least redundant and 4 being the most resilient. Tier 1 has little to no redundancy, and if the power goes, the whole site will go out. There'll be no backup power generation, and it's only useful for applications and systems that you're happy to go offline at pretty much any point. Tier 2, while it may still have a single path for power and cooling, there will be backup generation systems and some level of redundancy built in. Tier 3 introduces the concept of concurrent maintainability. This means that you can lose any one component or take one down for maintenance while still providing service through to the data floor and the applications. You may have a slightly lower level of redundancy while these components are out, but you will have failover and resilience in there. So you'll typically have a couple of generators, additional aircon units so you can take a unit off for maintenance, and some additional UPS. Tier 3 is the most common standard within the UK, which data centres align themselves to. Tier 4 is the top tier within the Uptime Institute's levels of tiering, and with that you're looking at full resilience throughout the entire site. So you'll have 2 completely separate power paths, 2 completely separate cooling paths, 2 completely separate network paths, and generally more than 1 feed off the mains grid. And this means that you can lose any component within the data center and you'll still have full resilience out to the data floor. Each of those power paths will have its own resilience in. So you can think of it like having 2 tier 3 data centers effectively, because you'll have tier 3 standard on each of those paths. There's very few tier 4 standard data centers, just because of the cost of adding in that additional level of resilience generally outweighs the benefits of doing things like good proactive maintenance and good testing of the systems. What you should really do is go and do your own due diligence. So go visit the facility and meet the data center team that are running it. Find out what kind of planned preventative maintenance they do, find out what testing they've got in place and what kind of monitoring they're doing. If they're doing things like full building blackout tests where a mains failure is simulated, that's really good for ensuring the generators are run properly and the UPSs are working effectively. Having a well-run Tier 3 data center will generally give you much better uptime than a poorly maintained and poorly run Tier 4 data center. Another good thing to look at is the overall level of resilience and uptime you need in your systems and applications. Just having your system in a Tier 3 or Tier 4 data center isn't going to guarantee you a certain level of uptime, and you should consider splitting your system or your applications across multiple Tier 3 data centers, and that way you can handle your failover and your resilience in the application layer, and you're not so reliant on the data center itself. Even a certified Tier 4 data center is only certified to 99.99% uptime, which still means you can have up to 29 minutes of unplanned downtime per year. So an application split across 2 Tier 3 data centers will give a much higher aggregate uptime than having it hosted in a single Tier 4 site. I hope that was useful and provided a bit of background to the tier standards you may have heard of when looking at data centers, as well as providing a bit of real-world context as to how you should approach them. If you follow the links in the comments section, you
Wow, so that was a pretty good explanation in terms of what tiers do. And he makes a very valid point there. You know, the cost of basically sticking it into a Tier 4 system, you might not be worth paying that extra, because you should probably look at 2 Tier 3 systems and do it along that way, or Microsoft Azure and the other ones out there, AWS, that will allow you to use regions and zones. Good. I understand you all can complete the section review if you're in Codio. So if you want to basically review those sections, tick the box and then show me a thumbs up when you've answered those, or if you have any questions. Look at that, a couple have gone straight through. Yeah, Bertrand's in there. Good ear. Patrick, fantastic. Well, I'll give you a couple of minutes, well, a minute, I guess, basically, to do those 2 questions. And then we can move on to electrical loads and basics. And don't worry, we will be having a 15-minute break. I'm not gonna grind you into the ground here. Okay, we're all good. Great stuff. Well, I think we'll probably plow on for another 5 minutes. We're quickly going to get through these things, and then we'll have our 15-minute coffee break. So we'll be ready for that in a bit. Okay, so let's have a look at electrical load. So what is electricity? Okay, it's basically forms part of a circuit. The power is consumed at one end. Tea time, right? Yes, you get some tea time, Greg. That's right. Another biscuit. Okay, so if you look at electricity, so every light bulb in your house requires power. You know, every computer essentially requires electricity to it. That is deemed by a power. If you look at your light bulbs, they're measured in watts. Now, watts is basically a function of power. So the bigger the wattage, the brighter the light bulb is the theory, to deal with LEDs and things like that. But the bigger the wattage, the more power it needs to basically drive it. Now, wattage is a combination of amps and volts. So it's amps times volts makes wattage. Now, I like to think of volts as basically being, if you imagine a waterfall, electricity basically coming over a waterfall, the volts is the height of that waterfall. So the higher the waterfall, the more force it basically has. Okay, so that's your volts, and the amount of water that can flow over the edge of that waterfall, that's your amps. So if you have lots of volts and lots of amps, you get lots of water running over the top. But you can also have a really high waterfall, so loads of volts, but only a small amount of amps that can get through it. And that then gets you something like the Angel Falls, which is in Africa, I want to say. It's Africa. See how good my geography is. Someone will correct me on that. So that's what you've got to think about when you talk about power in the system. So a data center, all your equipment tends to have a power rating, an electrical load that we need to know about. So we need to talk about an IT and a mechanical load. So the IT load is the amount of power being consumed by the devices that you're running. When we split this, we also have a mechanical load, which is the power being consumed by everything else that supports it. Okay, so you have your core stuff, which is your IT, your computers, your switches, etc. And then you have your mechanical load, which could be your air conditioning system, your lights, any extractor fans or anything like that, that basically is designed to support that environment. So we can divide this basically up, and that allows us to track what is being used where. Now we know we can reduce mechanical loads because we can do things like motion sensors for turning lights on and off. We can do sensible things like having balanced cooling system that work at a rack level to reduce the power, the air conditioning power that we're basically pushing in to cool a particular aisle. If that aisle is basically empty and not being used, why are we pumping really cold air into that? And efficient distribution boards allow us to work power through critical infrastructure. There's a question from Good. I love it. I love questions. Keep those coming. If we're building a data center from scratch, how can we accurately determine or forecast the expected power load requirement? Okay, because if you're building it from scratch, you are likely to know the air conditioning requirements for that building. Now, the reason I say you're likely to know that is because you work on averages. If you look at a traditional rack that you kind of go, in this rack, our traditional rack, I will probably put 3 data switches, and the rest will possibly be filled up with 2Us or 1U servers and possibly a blade system. So I can calculate an average of what I'm going to put into that particular rack. So that's a 42U rack that's in there. So I can then simply go, well, actually, in my data center, I'm likely to have this many of those particular racks available. And then that kind of gives me a rough balance of what I should have. And then what you tend to do is you double it. It's a simple, you kind of work with some fantastic numbers like that. A lot of it is guesstimates. You double it because you're working for future and not for what you currently think you're going to put in. And that's how you work it. So there's some good maths you can basically apply to it. Does that answer that question for you? Good. So this is how they work out the total, the power usage effectiveness, because we want to spend more power basically working our IT equipment. We want to get it so that PUE, our power usage efficiency, is better than possible. So the ideal PUE is 1, which would mean all power goes directly to the IT equipment. Okay, however, that's not really going to be the case. Most of the time, you're likely to get a PUE of about 45%. Okay, and that's pretty happy about that. And again, we just throw it into our particular data center calculations, and we do some numbers in there. You see PUE equals the total facility power divided by IT equipment, and we can do some calculations. So this is where we kind of build it up. Solar panels are definitely improved. Solar and renewable energy are getting good. So yes, that can definitely help with reducing the cost for your data center. But the maths is still the same in terms of the PUE. Where we get that power from doesn't matter. So it basically says in there that methods for improving the PUE using more efficient servers, so servers that use less power, such as blade servers, more efficient storage, more efficient networks. Optimize airflow and cooling. Airflow and cooling burns so much electricity, it's crazy. I say it's crazy. It does burn an awful lot. Making that more efficient is the way to go forward. Certainly, we will show you some examples later on. And certainly we'll show you when we do the air cooling and the air conditioning stuff that we will talk about on Thursday. Improving your building insulation. Yes, we don't want heat to get in. We want to basically keep all that out. Higher efficiency power and cooling infrastructure, advanced monitoring and data analytics, because you want to be able to control individual areas. You don't want to, just like your house, just turn the heating to however many, I've got to use English maths here. We don't want to turn your heating to 22 and just have your whole house at 22. Because hold on, I'm not using one of the bedrooms. Why is that not set to 15? Sorry, that's English money for you. That's degrees C rather than Fahrenheit. Okay, so power specifications. Okay. Power, we basically talked about it being volts. Essentially is measured in things such as kilowatt hours. When you get it from a supplier, they charge you in kilowatts. Okay, the total power itself is basically measured, or your voltage range. So you tend to tell them how much voltage you need, which is, as I say, the top of that waterfall. What I'm going to show you here is volts, amps, and watts explained. Okay, so we're going to let this guy chat through this for you.
So when you get your home energy bill, it lists the usage in kilowatt hours. But when you go to the store, you'll see things like 12-watt light bulbs, 9-volt batteries, and vacuum cleaners with 15 amps of sucking power. But what do these numbers even mean? I mean, why do we have so many different units to measure something that seems as straightforward as electricity? Surprisingly, the answer isn't just so appliance companies and physics professors can confuse you. It's because several important things have to happen in an electrical circuit for electricity to flow and for work to be done. You can think of a circuit kind of like the faucet on your kitchen sink. If you want water to come out, you need two things. You need the water itself and some pressure to force it through the pipes out your faucet and into your neti pot. Similarly, an electrical circuit uses electrons to carry the electricity, kind of like the water in our faucet analogy. But those electrons need something to push them along a circuit. This electrical pressure is what we call voltage and is often provided by two terminals, one with a positive charge and one with a negative charge. So on a battery, electrons flow from the negative end through whatever it is you're trying to power and then into the positive end where they'll stay unless your battery is rechargeable. If you're plugging something into the wall, this voltage is instead provided by your power company. And although voltage just measures how strongly electricity is being pushed through a circuit, it's important because many circuits are designed only to accept a certain number of volts, which is why the hairdryer you bought in Monaco might release magic blue smoke if you plug it in New York. So now that you know what volts are, what about amps? Well, in this context, amp isn't short for amplifier, but rather for ampere, which is a unit of how much electrical charge is flowing past a given point in 1 second. So when you put volts and amps together, you can tell how much current is flowing and how hard it's flowing. Multiply these numbers and you get, finally, our third unit, the watt. Let's go back to our water analogy for a second. Let's suppose you wanted to spin a small water wheel because you just like watching things spin, or I don't know, maybe you have it hooked up to a generator. Let's say you have a really powerful water pistol that forces water through a tiny nozzle. Even though the small nozzle means the total volume of water flowing per second isn't all that much, you wouldn't want to fill your swimming pool with it, the high pressure creates a strong jet that can spin the wheel easily. But suppose instead of a water gun, you have a much wider hose that doesn't push the water out nearly as strongly, but because the hose is a lot wider, more water flows per second overall, and the wheel ends up spinning at the same speed it did with your water gun. If we think of the hose and the water gun pushing out electricity instead of water, we could say that they're delivering the same number of watts. For a more practical example, let's say you have an 1100 watt power supply for your computer that's drawing full load because you're rocking 4-way SOI or something. So if you plug that into a standard 110 volt North American outlet, some simple math tells you that 10 amps of current is running through your power supply. But if you take that same power supply and use it with a 220 volt European outlet, you're only drawing 5 amps. But since the amount of power in watts is the same, your computer will work just fine in both places, even though you're using different volts and amps. Well, that makes sense, Linus, but why the heck then is my energy bill in kilowatt hours? Is that a unit of time? No, actually, scientists are just mean. It's a unit of energy. Watts and kilowatts express how much energy is consumed per chunk of time, something scientists call power, which is not the same as energy. But if you multiply a kilowatt by an hour, the units cancel and you're left with a number that shows how much energy that you hogged by running your air conditioner, gaming rig, and novelty lava lamp all at once. But what if you're more concerned about battery capacity instead of what's coming out of your walls? Well, if you're buying a replacement battery or a battery pack, you might see their capacity listed in milliamp hours, again, not time. Doing the math shows that this is a unit of charge, not energy or power. So going back to our water example, this is like how much water you have in a bucket, not how much is flowing or how fast is flowing. So a bigger bucket means you could charge your phone more times, and you can learn more about that and battery banks in this video here. So go forth then with your newfound knowledge and expertly buy the right voltage adapter, install the correct power supply, or just ace your electrical engineering exam if you want to do more with your life than work for some second-rate YouTube channel. But wait, what? Hey John, second-rate YouTube channel? Like, is that supposed to be a joke? It's not funny. Speaking of things that are no joke, Tunnel Bear VPN.
Well, I won't make much of the advert, but that's quite amusing, isn't it? Okay, that was good. I hope you all enjoyed that. We are going to have a quick break for 15 minutes. Well, I hope you all had a chance to have a little break, get a coffee, donut or a bicky. Oh, bicky, I could have done with a bicky. That's what I missed out on. And we're all ready to go for the next part of this data center electricity stuff. So let's have a thumbs up for everyone who can see the alternating current and direct current. So AC/DC, which is actually a rock band from Australia, I think they came from. God, I mean, that's showing, isn't it? Good, I can see you already. Good. Our fastest fingers first. Joshua in there, Mindy. Great stuff. Almost spilled a good brand. Man, I wish I was. No, okay. Let's not go down that road, shall we? Okay, so AC, DC. Difference between the two. Alternating current goes backwards and forwards, as we've seen. DC goes in one direction. So we won't get overcomplicated straight away, because we've got a lovely man who is literally going to talk us through some AC and DC. Within your data center, we've already said your computers all basically run DC when it gets inside it. These magic boxes, oh, see, I've got one here. Let me just pull one out. Ugh, this is out the back of a HP. Well, get into focus. So this is out of the back of a HP DR380. Okay, it is simply converting AC to DC, dropping it to the right voltage, the right amount of wattage that server will then actually be able to use. Okay, so that's what they basically do. But data centers, why don't we just transfer it all across to DC to start with? It would be much more efficient. But the problem is all manufacturing items still basically support AC currents. So we are moving across now where devices such as servers and other items will just simply take DC input. So that means we will convert it once rather than several times, as in each individual device. And you can imagine that a massive thing converting to DC will do better for us than lots and lots of these little ones. And one interesting thing is that, of course, when we kick across most data centers, when we kick across from our beautiful AC, from our mains lines, to our battery, which is DC, we have to convert that DC to AC to push around our data center, to then convert back to DC to actually run the silicon inside the machines. So we are literally converting DC to AC to DC. Okay, every time we run a conversion, we are losing between 5 and 12% of that electrical current. We know where that goes. That basically goes out in heat. AC power is a lot more efficient to run a large grid on. Yes, it is. That's why we use AC across all our grids. All our national grids across the world are basically run off AC. And it is the highway to hell. Thank you very much for that, Sonny. Okay, so let's let this guy have a little chat to you about the difference between AC and DC.
If you are looking for a video on legendary rock music, you might have found the wrong channel.
Can you all hear the audio? I just want to check you can all hear the audio in that. Yes, great. Okay, I'll let it go.
On a previous AddOhms video, we looked at voltage, power, and current, and you might remember this animation. One problem with this animation is that the voltage source shown was an AC source, while the current flow was shown as DC. So let's talk about the difference between AC and DC. The letters DC stand for direct current, and it generally means the electrons flow in a single direction. AC stands for alternating current, and it means that the flow of electrons change. Now this is where things can start to get a little confusing. This is an AC voltage source, so it's both AC and voltage. What the heck? How can voltage and current be the same? Well, it turns out we tend to use AC and DC abbreviations for voltage as well as current. So in other words, AC, voltage or current, is voltage or current that changes. DC, voltage or current, is voltage or current that is steady. Okay, so let's take a little bit closer look at these two, starting with DC. Check out this AA or LR6 battery. It provides 1.5 volts. This example circuit is going to be a DC motor like you might find in a toy car. When we insert the battery into the circuit, current begins to flow in a single direction, turning the motor. If we drew a graph where the vertical axis is voltage and the horizontal axis is time, we can see that the voltage at this point stays constant. Now, since this is a battery, eventually it's going to run out of energy and its output voltage will drop. So we know that the voltage will change over time, but the polarity will stay the same. So what is polarity? Well, polarity defines the positive direction, and for a battery, the positive voltage is created from the positive terminal. So what would happen if we turn this battery around? Well, that reverses the polarity, which means the current will flow in the opposite direction as before, causing our motor to spin in the opposite direction. Okay, so let's move on to AC, and in this case we're going to use a light bulb and a North American AC socket because, well, I live in North America. Notice how the circuit behaves when we turn the switch on. Let's break down what we're seeing by using the voltage graph again. Notice how the current is flowing in one direction, and as voltage increases, the light bulb gets brighter. Once the voltage reaches its peak, current flow stays the same, but the voltage begins to drop, and the light bulb gets dimmer. Once we reach 0 volts, the voltage's polarity changes, causing current to flow in the opposite direction. And again, as the voltage gets closer to its peak, the bulb gets brighter and then dims back down. Okay, we need to define a couple of things. First is, the change from start to finish is called a cycle. The rate at which the cycle repeats is frequency. Now, frequency is measured using the unit hertz, which means cycles per second. Different parts of the world use different frequencies for their AC systems, and it can either be 50 or 60 hertz. What this means is in 1 second, the cycle will repeat itself at least 50 times. Believe it or not, incandescent bulbs are actually flashing over 50 times per second. Now, it turns out that this rate is so fast that our slow human eyes sees it as constant light. In summary, while the abbreviations for AC and DC include the word current, they can be used to describe different types of voltage and current. DC voltages do not fluctuate, while DC current flows in one direction. AC voltages change over time, and the current flow can alternate direction. If you have questions about this video, please feel free to leave comments below. For more electronics tutorials, subscribe to this channel.
Okay, so all clear on AC and DC. Sounds great. Thanks, Victor. Christopher, is it true that electrons actually flow out from the negative terminal through the circuit and then back to the positive? In DC, yes, it does always go that way. Although we always like to think of electricity flowing from positive to negative, in reality, what we're actually seeing is electrons coming out the negative end and whipping round to the positive end. Because in the negative end, it's negative because there is more negative electrons. Does that understand that, Christopher? I remember a fun science lesson trying to get my head around that when I was young. See a couple of you typing, so I'll give you a chance to finish what you type, unless you just leant on the keyboard. And in a minute, I'm going to get a whole load of A's on there or something. Okay, so let's have a look. Single phase and 3-phase, triple phase. The negative electrons go out looking for a fight. Thank you very much. Positive. Well done. So single phase and 3-phase or triple phase, depending on which country you're in. Yes, single phase power basically has 2 wires that carry the electricity. Okay, it goes back and forth. Okay, this creates a voltage. Yes, and yes, you can see you've got an up, you've got a down, so it is variable in terms of the voltage. Okay, what triple phase allows us to do, triple phase allows us to smooth things out slightly. It also gives us a certain amount of redundancy. So if we do get a break in one of the cables, the other 2 phases of electricity will still be there, so we do not lose power. Okay, so the benefits really are there. So with triple phase, you can put a higher power load through the system because remember, power is watts. So we are now supplying it 3 times rather than once. So we can get a higher power, supports higher density computing systems. Okay, it allows it to be distributed across different phases and a better redundancy. So if we do lose a cable, the other 2 basically can pick it up and carry on. We can shut off one section, so we can do maintenance without downtime because we can kill one of the phases. The other two phases are still enough to support the power that we need. And it's good for supporting redundant distributed topologies such as PDUs, power distribution users. I can see there's a question there. What are the key technical challenges and additional maintenance requirements involved in the implementing DC power systems in a large data center? And how do these complexities balance against the higher efficiency of DC distribution? Well, that's a long question, isn't it? Involved in implementing DC power systems in a large data center. Well, the initial key challenge within a data center is basically with the devices that you're putting in. Okay, the majority of servers and the majority of indeed technical equipment is still running off of AC with its own individual transformer. So you have to physically go out and purchase those items that do support DC directly into it. So that's really one of the big ones. Triple phase means that we can basically, if we use triple phase, we get redundancy, which is where AC end of things is better to a certain extent. So how do we convert AC from AC to DC? I hear you all ask. So I hope you hear you all ask. Okay, so the big conversion issue is AC to DC. So when we take AC, we've got this magic wave, as you can see there. We've got a beautiful wave that goes up and down. What we do is initially we pump it into a transformer, and the transformer is designed simply to bring the voltage down to a current that we potentially would like to see. We then put it into a rectifier. Yeah, rectifier, Christopher, thank you very much. So a rectifier is the piece that then turns all that negative into positive. So all the pieces that are below the line that are negative, we're going to call it negative, reverse flow one, will now flip up because the rectifier change the circuit so that it is then going the right way. So as it drops to 0, the rectifier then goes, oh, I've got to switch the circuit around, and it pushes it up the right way. And then what we have is we have a filter circuit, and the filter circuit helps us smooth that top piece out because it filters out any of the jitter and allows us to basically then get a semi-smooth voltage. Now you can see, if you look at that voltage line now, there is a certain piece below what the filter circuit has done that allows us to look at it and go, hold on, there's a smooth DC piece there. And that's what the regulation circuit comes in and does. So it basically puts it in there and says, okay, I'm only going to take everything below this voltage and use that. And that gives us a smooth DC output. But you can see from this example here, we've moved from 220 volts AC to 5 volts DC. And we tend to lose between 5 and 20% if we do that. Now, of course, we might as well. We can't talk about going from AC to DC without going the other way. DC to AC, it's a simpler process, should we say. That's probably harsh of me to say that. But what we basically have is converting DC to AC is we have to fake the wave. So we fake the wave with the circuit. You can see on the left-hand part of the diagram, when the blue piece connects through to the blue, it will then push it one direction. As that disc spins, we then get the blue circuit connecting from the top red item. And that pushes through. And that then allows us to create the AC wave. Now, in the cheap systems you buy, it will actually create a square. God, my eyes are going funny on those squares and those wiggles. So it will create a square wave because it is either 100% of the DC current or negative 100% of the DC current. Okay, there are items out there. If you spend a little bit more money, you will get one that will give you a nice smooth AC current. Any questions around AC to DC conversions and DC to AC conversions? So the main thing to remember is that we do lose Every time we convert, we lose. So there's a section review there. So far we've gone through, we've talked, you know, about the power and stuff, and we should be able to answer these questions here. Is there 2 or 3? 3 questions. If you could do that in Codio, that'd be much appreciated. And give me a thumbs up when you've managed to push all those in. Thank you very much, Daniel. Fastest fingers first coming up there for you too. Well done, Mindy. Well done. Frodo, great stuff. Yeah, I'll give you all a couple of minutes basically just to finish that off. If there's any you'd like to ask questions about, please, as I say, do throw it into the live chat. See several people type in thumbs up coming through. Okay, we're going to click through then, and we're going to carry on now. I can see lots and lots of thumbs up in there. That's great. If I am moving on a little bit quicker, then too quick for you, let me know. Where is the question? Oh, okay. Good here, the PUE, remember that was that value, that rating that we gave ourselves, which is a comparison between electricity we are spending on the IT devices, as in the servers and the switches and the critical things for our system, compared to the amount of electricity we're spending on things like air conditioning and lighting and any other security devices that we have. So it's that comparison between the two. So anything that basically allows us to increase the amount that we're spending on IT basically means we're reducing the amount that we're spending on other things. So essentially reducing the power consumption on non-computing devices would increase our PUE value. Does that explain that for you, Kadir? And then tell me if I've pronounced your name totally wrong. Daniel, thank you very much. There's the magic formula. So we reduce the total facility power and increase the IT power equipment. Good stuff. Okay, I'm going to shuffle on then if that's good. Thank you very much, everyone. So we're going to drift into maintenance. We know maintenance is so important. We are running electrical systems. Do we need to do a great deal of maintenance on these things? Electrical cables don't need a massive maintenance, but they can fail, so we need to check them. The important things we need to check are what happens when power failures happen. Okay, so general causes of outages are going to be power failures. Okay, so that is a fairly significant amount. IT equipment faults, yes, we know systems go wrong. Our servers, our storage devices are potentially going to fail. Okay, they can crash, there's software bugs, and indeed just general hardware failures. But human errors are the biggest source of failures. Okay, I know it's a horrible thing to think about, but we get things wrong, and we all know we get things wrong. So human error causes about 70 to 80% of outages in data centers. Okay, most of this tends to roll up to processes. When you work as a data center technician, you will not be given a handbook. It's no longer a handbook. You will basically have processes that tell you how to do things, when to do them. So for example, a good example is if you are asked to change something like a disk drive in a server, you will have a process that tells you to make a note of the the device name that you're basically going to, the rack it's in, the U that it's basically in. It will then ask you to walk around to it. It'll then ask you to confirm that the light is red and not flashing green on that particular device you've been asked to change. And there will be a whole process stuff that goes along there in terms of clicking it, pulling it out, swapping the chassis over, putting it back in, and then basically bringing that back up. Okay, so if you follow that process, yes, things work great. Things work fine. If the process is wrong or the process is faulty, then we as humans make errors. Okay, we carry the can for it. Well, there's a classic example over at iMart when I was working in that one customer contacted the NOC staff and said, can you please power down this particular server? Okay, so the guy basically looked at his process and he went, okay, what I've got to do is I've got to go to this rack, I've got to go to this U, and I've got to take the power out the back of it because that's what he's asked me to do because he said power it down. Because he couldn't find an on-off switch, so he's powering it down, I'm going to pull the cable out the back. What he didn't realise was that he was actually dealing with the blade system because the process didn't handle blade servers. So instead of pulling out a single server, he literally dumped 12 blades. So we dropped 12 blades. If you don't know what a blade server is, I'll show you later. Okay, so again, it's following that particular process. They will have what's known as a MOP, a maintenance operation procedure. And these are all online now. So a lot of data center technicians will wander around either with an iPad type or a tablet type device or a laptop, or they have chassis that literally have a server, not a server, have a PC with a wireless connection and a UPS battery plugged into it. And they'll wheel that round to a variety of locations with the operating procedure and they'll look at it and they'll follow it. And that's how it works. No maintenance and audition is a quick trip to fail. Yes, it is very much, Victor. If we do not test things, we fail to test, don't we? Kadir says, why is it important to regularly test standby generators under both loads and non-load conditions? You like to do it under load because it's live, because you are not only testing the power generators, you are testing the connection that goes back from the power generators that feeds into your transformers, that feeds into your data center. If you do it non-live, then potentially there could be a fault in that electrical cabling that leads between your generator and your power units. And that's what you're trying to do. You're trying to do a whole system rather than just go, yeah, I can start the car. It's like saying I can start the car, well, that's great, but can you drive the car anyway? So you can start the car every couple of months, but will it move anywhere if you're sure you want to move it? No, let's start it, let's drive it, and then park it up again. So that's really what we're doing there, Kadir. Any questions about that? We will drift on to preventative maintenance. I can see that he is typing something in there. So we have preventative maintenance, which is here we go, B. What should the guides have done instead of unplugging the cable? Okay, blade servers are if you can imagine an entire server is normally a rack, a single rack server. A blade system is multiple servers that literally slot in next to each other. Okay, to unplug or power down one of those, each blade server has its own power switch on the front. You can also, just like you do with a disk drive on servers, if you've ever seen those, you can also just pull it out. So you can pull out a blade server, that powers it down, plug it back in, there you go, that's a reboot. There is actually an on-off switch on the front of it. Blade, thank you very much, Daniel. So that's what a blade server looks like. That entire U, that 4U blade server, is individual servers, each one of those. They don't contain many disks, but they do a lot of processing. So pull it out, push it back in again, reboots an individual blade on that server. Does that make sense, B? Thank you, Daniel, for the image. Very nice. I'm holding for B. Yes, thank you. Perfect. Okay. So performing regularly maintenance, just like on your car. If you regularly maintain your car, you change the oil filters, you change the oil, you change the air filters, you do the spark plugs every now and again, will mean that your car will run all the time. So we test standby generators under load and non-load. So we make sure they work. We replace the oil in the generators. We inspect and test the UPS systems. Walking into a battery room, smelling the amount of caustic stuff that comes off a battery room is incredibly fun for the first time when you do it. But yes, checking the batteries are at the right voltage, putting some load on the batteries to make sure the batteries aren't worn out. Okay, the acid is still working in them and they're still basically holding electrical charge. Okay, so you put a bit of a power load across them and then see basically how long they can maintain their full voltage. You can do things such as infrared scanning of electrical gear to make sure you can see any particular heats, because electricity, no matter what we do with it, generates heat. Even if we're passing it through some of the thinnest cables, or thickest cables rather, will generate heat. So if we can do some infrared scanning, we can see where the heat is being generated. And potentially that means there's cable breaks, because that means the cable has got thinner over time. We can also do things such as power audits. Okay, power audits allow us to basically check what we're doing in terms of, do we have enough power for running the building? Is our backup generators going to cope with it? Okay, so we can regularly perform these power audits, and a lot of these are done automatically. So we have power monitors that monitor where the power is going and how close we are to that critical limit. We tend to do this in 3 stages. So we do a building management system. So we check the building management system, which basically provides real-time monitoring of what electricity our building is using. Okay, you can analyze that and you can work out, are we getting close to the knuckle? Do we need to increase our power? Do we need to increase our backups? Then we can do an electrical power monitoring system, which simply meters particular areas, so different points of the infrastructure. So you may do an electrical power monitoring on a room that then has loads and loads of racks of servers. You may do an electrical monitoring on, for example, all your communication gear that lives in its own secret room under heavy lock and key. Okay, but you can basically do some detailed analysis and helps optimize what you're basically doing. And then we can do a branch circuit monitoring, which is really talking about individual circuit breakers. Now, a circuit breaker is essentially one line of cable that comes out of your fuse system that will run across your aisle, probably feed 9 to 10 racks. 9 to 10? It's the wrong number. 10 to 15 racks. So basically field a line of your racks. So we can get granular. And because we can get granular, we can work out what we're doing. If we have a line of servers, a rack of servers that is drawing a shed load of power in one system, next door to it, we've got one that's basically doing nothing. We've got to think, hold on, would it be smart to move that across so there's less power draw across that individual line? Yes, that would be perfectly sensible. And that way we get more distribution and it'll help with our air conditioning as well. So some of the best practices are watch out for hotspots, which include potentially strange circuits. We can look for the balance of power across the PDU, so power distribution units. This is me talking about that server rack that is basically drawing way more power than the one next to it. So across your PDUs, balance them. Don't put big power stuff next to each other constantly. And look for the actual power draw versus what you've designed the building for. And look for proper redundancy across A side and B side power sources. Remember I mentioned A side and B side? Well, I didn't mention A side and B side. I mentioned multiple power sources coming in. So most server racks, you will see, will go across a building. Okay, and at the end of each rack, you will have a power distribution unit. You have a power source. And these tend to be called A side and B side. And a power cable will go to the power distribution unit from the A side, so that feeds every single rack, and from the B side that feeds every single rack. Most devices that are put into systems have two power supplies. And the reason they have two power supplies, well, part of it is for redundancy. So if this power supply pops on my HP DL380, the other power supply will kick in. The system will run at slightly less power, so it'll not be performing quite as quick. But I can basically plug this in and out. This is a hot plug and play. So my system will now be running off one power supply unit. So my NOT guy will literally grab one of these from the room, run round, slot it in and change the cables over. And then it'll come back on. So that's A and B side. But you can imagine if one of these trips, you could lose the whole of A side. And that affects everything in that rack. So every system really needs to be plugged into an A and a B side, which is why we have A and B side for power distribution unit. Any questions around that? Oh, great stuff. Here's a question then. Okay, Gadia says, during a monthly power audit, what specific methods or tools do technicians use to identify hotspots and evaluate circuit balances? Okay, when we talk some hotspots, there's two ways to look at a hotspot. You can use infrared, which basically allows you to see the cables that are getting warm. That means they're drawing more power. The more power that goes down a cable, the hotter it gets, and therefore we can pick it out like that. There's also a whole load of electrical monitoring tools that are basically put on. You can either clamp them around cables, or you can have a PDU that's basically got some monitoring systems on them. Mate, there's no such thing as too many questions. This is fantastic. So you can have some circuit balancers that basically measure the output from each circuit, and that will give you some nice, pretty graphs, essentially, is what they give you. And that will tell you where your power is being drawn to. And that's what you basically use for when you do those audits. And normally, if you have a data center that is constantly changing in terms of your racking and re-racking items and moving them around, you normally reckon you do a power audit once a month. Okay, if you have a system that's fairly stable and nothing new is going in and things are running fairly statically, then you can kind of stretch it out and do it once every 6 months. But that's the general idea. As I said, no such thing as too many questions. You've been a star today. Okay, so any further questions about power AC? So we're going to drop into this. I can see someone type in there. Sunny. Let's see what Sunai. Sorry, Sunai. I got that wrong earlier on. He corrected me. Thank you very much.
It's Sunni.
Sunni. Oh, my apologies. Thank you very
It's
much for
Muslim.
unmuting. I was going to get that wrong
It's
all week.
Muslim. It's Native American, and I forgot what it means in Korean.
Oh, okay. Thank you very much, Sunni.
No problem at all. None at all.
Okay, there's another question there that says, what design considerations ensure the A side and B side power feeds remain fully independent? The way we make it independent is we either do something clever with color-coded cables, or we basically use separate PDUs. Normally what we do is you have a power distribution unit, which is essentially what your plugs go into, on the left-hand side of a cabinet, and one on the right-hand side of the cabinet. And you go and you label it, this is A and this is B. And then your server, you take one cable that plugs into A and one cable that plugs into B. And then you kind of go, when you're racked, you kind of know that's good. So that's how you kind of make sure they're independent. Does that answer that one for you? Good stuff. Okay, so there's a section review, which will cover, things such as the human error, the prevention and maintenance questions. You can click through that in your Codio. And then as soon as you've gone through that, give me your thumbs up. Great stuff. A lot of you are cracking through those. That's good. God, we're all smashing through. Thank you very much. Joshua, Mindy, Bertrand, Christopher. I'll give you a couple more seconds or a minute or so to do that. We've got bags of time today. It's been a great lesson to actually run today. B, I hope we managed to get the explanations right for you and you understand it all. Great stuff. Okay, so before we drop into some form of conclusion over that, I thought it'd be interesting if I shared a couple of what I consider to be, I hope you find interesting facts around electricity and power. There's a few of you who are not that familiar with it, but let's have a little look at these things. Okay, so danger. We know electricity is dangerous for us. These are some fantastically good stats. Yeah, Kadir's asked another question. Thank you, Kadir. Please do keep asking these. When it comes to preventing human error in data center operations, do you think regular staff training, such as monthly sessions or biannual refreshes, is an efficient approach? Yes, it is. Good documentation is also perfect, and people not shortcutting. The part of the fun with some of the data centers you have is you will produce a policy document, a policy for doing a particular task on a particular server. And that's fantastic. And that gets written and then it gets filed. And then everyone looks at it twice, 2, 3 times, and then goes, I know how to do that. I'm not going to look at it again. Then what happens is someone puts in a totally different server with a totally different configuration with totally different requirements. And that not technician goes, I know how to do that. I've done it hundreds of times before. Doesn't look at the documentation, goes to that server, does what he thinks is right, but is only right for the other server. And then all of a sudden that one falls over and there's something wrong. So there's always a case of when you asked to do something in NOC, just check, quickly check, you've got time, quick look, check it hasn't changed, and then go and perform the same task. Okay, so it's all about that double checking because there's no way that we can constantly refresh it. Yes, you can do refreshing training courses, which is great, and it's definitely worth doing it. For mission critical things, such as power generator tests, when you're doing full tests and things like that, you normally qualify the person to basically do that full generator test, but you would then basically make sure that someone goes with him. So you buddy up. When you're doing anything mission critical, buddy up. There's 2 of you there. One of you looks blankly at the other one and goes, I'm not sure what we're doing. Then you both go back to the operations manual and double check it. Okay, and it only takes one of you to be slightly hesitant that you both go back and check it. Okay, so it's always better to be safe than to drop someone's system. Does that make sense for you, Kadir? Great stuff. So we know electricity is dangerous. How dangerous is it? Okay, we know it will kill you. Okay, so 0.1 milliamp for 2 seconds through your body will kill you. That is deemed to be the lethal dosage of electricity. Now, as soon as you start thinking about that, hold on, a milliamp. What's your average phone charger produce? What's your average phone charger produce? You know, some of these sockets we have, you know, they're 2 amps, aren't they, on your charger socket? Two amps in the charger socket. But what you've really got to look at is it's the voltage as well. So the amps, they say the ampage will kill you, but you need to have the voltage to drive it through. So it will take 50 volts to basically get that electricity through your body. Who's ever seen one of those 5 amp square batteries with the 2 terminals on the top? We've all seen those, haven't we? Who's ever had the fun of actually putting it on your tongue? Okay, that's not killing you because the voltage isn't enough. Okay, we all put it on our tongue, we get a tingle, it's great fun. We stick it on our arm, it does nothing because there's no liquid there. So the voltage isn't high enough to pass the electricity through that. The reason it tingles on our tongue is because there's water there, and water is a better conductor than our skin is. 9 volts, so a 9-volt battery, isn't it? Yeah, little double D battery, 9 volts. So you can see there that we need basically to have both the volts and the amps, although they say the amps will kill you. But data centers, which is when I was a kid, with a screwdriver in my hand looking for power, oh, don't. Scares the life out of any parent. We protect it. We are protected by what is known as an RCD protection. Now, we know we've got fuses, haven't we? We've got fuses around the world, around our systems, and the fuses will go if the ampage is above a certain amount. So in the UK, we have electrical light ring mains that are at 6 amps. So if you draw more than 6 amps, that fuse will pop. Okay, but you've just told me, Dave, that the 0.1 milliamp will kill me. Okay, so what we do is we do a different protection for that. We do an RCD protection. So an RCD basically measures the difference between the power going out and the power coming back in that ring. And if that is different by a significant amount, by even a small amount, we know there's a breach in the circuit. It's not just powering a device, there's a breach in that circuit. That breach in the circuit will pop an RCD fuse system. So that's what protects us. And that is below 0.1 milliamps. And when you buy a fuse, you will see they are rated to particular things. So that's how we protect ourselves. Not necessarily with the fuses on the left-hand side, but with the RCD circuits. That's why they're really important in both domestic as well as in data centers. You will see RCD circuits in data centers, which will cut things out. Anyone want to ask any questions about RCDs? Yeah, it's pretty good, isn't it? And then some beautiful numbers for you. Who's ever played a shock game? Oh, shock tanks or that other one? This one's a simple handle one we're showing. So the shock games we use, they're up to 140 volts, man. They're so funny. They're so tingly. But because they're generally just going through the hand, it's not going to kill us. It needs to hit the heart area. But as you can see, they are great fun. So those are some statistics. Domestic power supplies, your sockets normally in the UK. Don't know how many people in the UK here. Is that rusty grey thing an RCD? Ah, the rusty grey thing at the top is, yes, sorry, that rusty grey thing. That little section there, that red piece at the end, that's your RCD. As well as this and this. Okay, so those are basically RCDs on the system. And that RCD will shut off all of these fuses. It won't flick them all, but it will basically kill all the electricity to all those fuses. So if there's a fault in any one of those circuits, the RCD pops and you lose the lot. So as I say, domestic power supply socket, 16 amps, light rings, 5 amps, cooker, 32 amps. Okay, other devices can have more. If you've got power showers, they're probably more. That's UK, so we run 240 volts over here. So US, you run 110. So you can imagine that potentially your cooker socket in the US might be a bigger ampage on that. Lightning, 300 volts, 30,000 amps. That will kill you, that's for sure. Or at least leave a mark, won't it? Any questions about some of those numbers that I've just thrown in there? Okay, that's good. Oh, there's a good question. How many types of RCDs are there? There's loads of different types of RCDs, and the RCDs all have different ratings, which are based around the amount of milliamps that is milliamp change detected and the speed at which it cuts off. So there's two ratings for RCD circuits, the milliamp detection of change and the speed it is designed to cut off. Great stuff. Okay, so we're coming towards the end. We've had a bit of a conclusion here. Let's run through the conclusion quickly. So we basically talked about power distribution. We've talked about how it comes from the power stations through substations. We've talked about our redundancy power supplies, which is our backup power sources, such as our generators and our UPSs, which are essentially big battery times. We talked about how we consider things such as uptime. So higher redundancy produces uptime. So the more backup systems we've got, the less time we're likely to drop. So therefore, the more uptime. We've also mentioned things like our load, our power consumption by IT, and we did our magic mathematical equations there, comparing the IT usage and the mechanical usage, and that gives us a beautiful PUE number. Single phase versus triple phase. You're working in a data center, it's all going to be triple phase when it comes in to give you that extra maintenance. And then the maintenance, what we need to follow, things we need to check. Worn cables need to be noted, as well as things like leaking fluids in the generator systems or anything else around there. And power audits that show us how we are managing with our power systems. So I thought at the end we'd just have a very quick quiz.